All right, welcome to our second set of notes from Chapter 5 on the calculation of properties. In this set of notes, we'll briefly talk about reference dates. So in addition to this PowerPoint style presentation on reference dates, know that there's an additional video in which I work through the two common reference dates used as if I were on the whiteboard. The reason for that is hopefully it gives you a different perspective of me actually working through the equations. Reference dates is something that often causes students trouble, and not really trouble, but confusion, and it's kind of not necessary. And so hopefully by going through the equations, they make sense. All right. So the whole idea behind reference dates is, so far we talked about the first law of thermodynamics in chapter 3 and the second law of thermodynamics in chapter 4. Okay. And so, what should be important or what you should know by now is thermodynamics is all about differences. If I think about my first law of thermodynamics, it's delta U is equal to Q plus W, right? Or its differential form, du is equal to del Q plus del W, right? We don't write delta Q and delta W because they're path functions, okay? But it's delta U, right? It's a difference in internal energy, okay? Same thing with my definition of entropy for my second law, right? ds is equal to del Q reversible or dQ reversible over T, right? So it's all about differences, right? Thermodynamics is all about differences, calculating differences in my properties for a given process, right? For a given path. And so in thinking about that, right, absolute quantities really don't matter, right? So it's all about calculating differences. But oftentimes, it's convenient to define absolute properties, such as when we tabulate data, say in your steam tables in the back of the book. Right? So the absolute value of a property in general isn't significant because as long as properties are defined with respect to the same common reference date, that common reference date will cancel out when we calculate differences. All right, so now when we calculate reference dates, okay, again, so all the equations are typed up here. We'll have another set of notes in which we work through the equations explicitly. Okay, but let's kind of see how we might define a reference date. Okay, so here I just have an expression, so I'm going to calculate enthalpy, right? So I'm writing my enthalpy as the sum of my ideal gas plus residual term. Then H naught is going to correspond to some I don't want to call it some reference state, but some state that I'm going to define H relative to, right? So in state naught, right, H naught is equal to H naught ideal gas plus H naught residual. So H here, right, is going to correspond to my enthalpy in my state of interest. Okay, H naught is going to correspond to some other state. Okay. All right, so if I want to calculate the difference in my enthalpy relative to my enthalpy in state naught, right, H minus H naught, the difference in my ideal gas terms plus the difference in my residual terms. So I write the ideal gas term as a delta H ideal gas. The residual term I just keep as HR minus H naught R because when we use our equation of state, right, we calculate HR and H naught R, right? We don't calculate a delta HR. All right, so they bring H naught over to the right-hand side, and I have this. Delta H of an ideal gas is just integral from T naught to T Cp ideal gas dt. Then I have my difference in residual terms in H naught. All right, so this is me trying to get an expression that looks like the absolute value of H. So now to calculate the absolute value of H relative to some state H naught, okay, we're going to define our reference state in two different ways. Okay, state 1, right, is going to be H naught. We're going to define H naught to be 0. Okay. So in convention 1, okay, we define H naught as being equal to 0. Okay, so imagine I'm trying to tabulate data in the steam tables. Right, so typical convention is to take our 0, our reference state, to be water at its triple point. Okay, and so we'll take the enthalpy and entropy of our fluid to be 0 at the triple point. Right, and we'll calculate everything else in relation to that. Right, and so so the steam tables use convention 1. All right, they would pin down some state in which I'm going to define my enthalpy and entropy or my thermodynamic properties to have a value of 0, and then I would calculate everything in relation to that. So I would get what looks like an absolute H as being really my actual property relative to that idealized state, which I'm taking to be 0. So from this formula here, if I take h naught to be equal to 0, then h is just integral from t naught to t cp dt plus hr minus h naught r. Okay, so what I'm trying to do here is I'm trying to define something that looks like an absolute value of hr, and I'm doing that by defining some value at some reference state to be 0, and then I'm calculating everything in relation to that. Okay. Convention 2, okay, isn't to assume that h naught is 0, but to assume that h naught, the ideal gas contribution in state 0, is 0. And how that simplifies the equation is, well, h naught is equal to h naught ideal gas plus h naught r. So if h naught ideal gas is taken to be 0, then h naught is equal to h naught residual. So if I go up here and h naught is equal to h naught residual, this kills this, all right? And I'm just left with h is equal to integral from t naught to t cp ideal gas dt plus hr, right? Where in general, these residual contributions I can calculate using my cubic equation of state. So again, the big takeaway with reference states is in thermodynamics, all we care about, right, in general, all we care about are calculating differences in properties. But there are occasions when defining something that looks like an absolute value can be of convenience or can make life easier, such as tabulating data in the steam table. And so here's the two common conventions used when defining a reference state: taking an actual value at some state to be 0 and defining everything in relation to it, or taking the ideal gas contribution to be 0 at some reference state. Okay, and then we define everything in relation to that. And what's going to be key is that as long as you define, so if you're using these absolute values, as long as you define your reference state consistently throughout the problem, when you take differences in your property, that reference state cancels out, right? So it doesn't matter, has no significance on the final result. But you need to make sure you're consistent. Okay, and so here's the cover info for Appendix E in the steam tables, right? And if you notice, right, they tell you the reference state is the saturated liquid at the triple point. Okay, and so they're defining their 0 as a saturated liquid at the triple point. So everything's defined, right, in relation to that point. And why the triple point, right, just to take things further, is Gibbs phase rule. So triple point corresponds to water at vapor, liquid, solid liquid equilibrium. So if I have a single component system at 3-phase equilibrium, I have 0 degrees of freedom. So just by saying I have water at the triple point, the state of my system is fixed, right? So there's no question whatsoever with regards to the state of my system. And I'm taking my liquid properties, so the enthalpy of my liquid and entropy of my liquid, to be 0, and I'm defining everything in relation to it. Okay, so it's this first convention, h naught is equal to 0, and we're defining everything in relation to it. Okay, hope that helps. Again, have a look at the screencast in which we work out the details for additional information. Let me know if you have any questions, and look forward to seeing you as we work through some example problems.